in this example, we're going to see how we can sketch the graph y equals -3 square root of half of x plus 2 plus 1. So every transformation we could have is almost here. So I just have some graph paper off to the side. Okay, so a couple questions to figure out first is the parent graph. We'll state the transformations. We can use a little table of values to figure out the points one by one to avoid making mistakes, which is always good. And then we'll graph it. So, what's the parent graph? What's the parent graph of this function? Yep. Great. Y is equal to the square root of x. And let's figure out all the transformations. So a is equal to -3. What does that tell us? Tells us two things, right? What does that negative tell us? Reflection. Good. In which axis? Good. Okay, and then the value of 3 tells us it's what kind of transformation. So we have the reflection, and it's also a stretch. What kind of stretch? Vertical stretch. By a factor of 3, I'm just going to say of 3. So we could think about what's happening with these points. It's kind of like a table of values, but not exactly. So we started off with 0, 0 with the original function. So let's graph the original function. Hopefully you're comfortable with all the parent graphs now. Try to remember the key points. So for the square root, it's 0, 0. If I take the square root of 1, it's 1. The square root of 2, square root of 3, they're kind of hard to graph, so I wait to get to 4. The square root of 4 is 2. And then the next easy point is 9, because the square root of 9 is 3. But we don't have that much room on our graph, so we'll just use these 3 points. Okay? So when we reflect it, we're doing the negative of all the f at x values. So when we do the negative of all the f at x values, when we had originally a 0 for x, and we had a 0 for y, negative of 0, 0, doesn't really change. Our x value is 1. This isn't affecting the x values, it's only affecting the y values. So f at 1 is 1, so negative 1. So I'm kind of doing something here in my head that I'm not really explaining, and I'm going to write it off to the side here. So notice I've said that we're finding negative f at x, we're finding the reflection. So negative f at, and my x value is 1 originally, f at x here, f at 1. So negative f at 1 is equal to negative 1, because f at 1 is equal to 1. Too many ones, it's hard to follow. Let's do one more point and maybe it'll make more sense. So in the original function we had the point 4, comma 2. Now we're doing the negative f at x value. So we're doing the negative of f at 4. What's f at 4? F at 4 is equal to 2, right? So negative f at 4 is equal to negative 2. Does that make sense how I'm using the function notation here to express the y values? I know we've just started with it, so negative, nope, 4, comma, negative 2. So we just took all of our y values and made them negative. When we graph it, all the y values are the same but negative numbers. So what we've really just graphed here is y equals negative the square root of x. We did the reflection. So next we should do the the vertical stretch. So my usual way to do it is looking at the graph. I usually look at it, I say, okay, it's a vertical stretch. It's going to get further away from the x-axis. So I need the point to be 3 times further away. Right now this point's 1 space away from the x-axis. I'm going to make it 3 times further. So 1, 2, 3. That's 3 times further from the x-axis. This point here is 2 away from the x-axis. We want it to be 3 times further away. 2 times 3 is 6. So 2, 4, 6. I've just stretched it by a factor of 3. It's 3 times further away. Okay. We could also use the function notation to write out the points, almost like doing a table of values, but it's a little bit compressed here. So these points, I just found them by looking at the graph, but if you're more comfortable with like a numerical approach, you could do it like this. So all my y values are now 3 times what they were previously. 0 times 3 is still 0. We had a -1. Now we're going to triple that. So it's going to be, we had a 2, a -2 once we did the reflection. Now it's going to be, what's it going to be? -6, I heard. Okay, does that make sense? Thank you. Where's the candy to throw at? To you. So let's do the next transformation, and we have a k value of 0.5. So no reflections. What kind of transformation is a k value of 0.5? Is it horizontal or vertical? Horizontal, good. Is it a stretch or a compression? It's a stretch, that's right. Okay. So we could do it just by looking at where we were with our transformations, and we can apply this transformation, or we can do it with the points to figure out the points numerically. So I'll do it both ways for you. Really, you only have to do it one, but you can always use a second method as a check. So everything has to be horizontally stretched by a factor of 2. So I have this point here, and it's going to be horizontally stretched. It's going to be twice as far away from the y-axis. Right now, it's 1 away from the y-axis. Twice as far would be 2 units away. So this point has just been stretched away horizontally. This point, I'm going to run out of space on. Maybe I'll just zoom over here. How far was this away from the y-axis? It was 1, 2, 3, 4. So now it's going to be 8. 1, 2, 3, 4. Approximately right there. Okay, so now we're up to y is equal to, write it over a little bit. Y is equal to, what transformations have we applied? We applied the negative, we applied the vertical stretch of 3, and the horizontal stretch. Okay. Point-wise, we could figure it out as well. Not a lot of space there. So basically, it can take a little bit of time to grasp this idea here. We have to think about what we're putting in to the function. What's going to go into the function. So for this next one, I would like to have an x value of 1 to be able to figure out a y value. What do I have to put into this function so that I would have inside the function a value of 1? Does that make sense? So I'm going to put a value of 2 here, and then I'm going to show you what I mean. So negative 3 times f at 0.5 times 2. If I pick an x value of 2, then using my function notation, I end up with f at 1. I know f at 1. F at 1 is equal to 1. Right? So I chose my x value on purpose so that my input into the function would be 1. And my y value is -3 still. This transformation was a horizontal transformation. It didn't change the y values. It only affected the x values. Okay? So for the next point, I would like to put in a value of x so that inside the function I'll have a value of 4, because I know that if the x value is 4, I know the y value is 2 before the transformations. So what can I put in to the function? So when I multiply it by 1/2, I would get f at 4. Yep. Great. Okay, because when I take half of 8, I get 4. And the y transformations didn't change because it's still -3 times f at 4, which was 2. So -6. And that's the point we had over here. This point should be 8, -6. Let's count it out, make sure it's all right. 1, 2, 3, 4, 5, 6. Perfect. Okay, so what we're doing numerically matches what we are doing graphically. Okay, kind of showing you two different approaches at the same time. I like to just look at the graph and figure out the points, but this is a good way to do it as well. What's the d value? What's the d value? So the d value is actually -2. It always has to be written in the form x minus the d value. So we have to rewrite this x minus -2. Do you remember that from last year? Is that a concept you talked about last year when you did the transformations? Maybe a little sketchy on it. Now we can read the d value exactly, because we say usually, if we just go up to the notes quickly here, when we were talking about the transformations, it has to look like x minus d. X minus d. It didn't look like x minus d, it looked like x plus a number, so we have to make it x minus a number. So d is -2. Okay. Is this moving 2 to the left or 2 to the right? 2 to the left, 2 to the right. 2 to the left. So it's horizontal, translation, left, 2. Okay, so I can take all of my previous points that I had and just move them 2 to the left, which is good because I was running out of space, so I'm really happy with that. So my 0, 0 is going to hop over 2 spaces to the left. My point here, 2 to the left. My point here, 2 to the left, 1, 2. Great, everything fits better on my graph paper, I'm happy. Okay, so this function that we have right now, it starts here at -2, 0 and continues down. And so far we've graphed the reflection, the vertical stretch, the square root of 0.5, and the x plus 2. What's left to do? Yeah. Good. Vertical translation. Good. Do you guys want me? Do you want me to show you point-wise how we would deal with the transformation we just did before we move on? So now we're up to -3 square root of 0.5 times x plus 2. So basically, what we're doing to all of our x values is we moved them 2 to the left. So what you're asking yourself is, well, what do I have to put into this function so that inside the function would give me a 0? Because if inside the function is a 0, I know f is 0. Kind of confusing how you think about it, sort of like working backwards. So if I put in a value of -2, that's a 3, -2, then -2 goes in, we get -2 plus 2 is 0, times 0.5 is 0, square root of that is 0, times -3 is 0. So all of our x values are going to go down by 2. So here we had an x value of 2, it's going to become 0. The y values don't change. It was 8, it becomes 6. The y values don't change. So the last transformation is adding that 1. What color haven't I used here? So c is equal to 1, and it's a vertical translation up 1. Negative 3, all the stuff we had before. Some people do both of the translations on the same step. That's fine. You can do that. So the x values are not changed here, only the y values, and they all go up 1. 0, 6, negative 5. For me, instead of doing it point-wise, I would rather just do it on the graph. I'd rather just look at it and move every point up 1. Do you guys prefer looking at the graph and doing the transformation? Or do you prefer a numerical approach? So now we finally have our final graph. Y is equal to negative 3, square root of 0.5, x plus 2, plus 1. I think this is the only example I did where I have every single possible transformation. And again, you want to check that that works, sub in some values. So I say that this is at negative 2 comma 1. Negative 2 comma 1. Is it? Double check. I put in a value of negative 2. Negative 2 plus 2 is 0. Times 0.5 is 0. Square root is 0. Times negative 3 is 0. I get a 1. That point checks out. Do a quick table of values. Make sure you're right. Okay? So example number 2. If f at x is equal to the absolute value of x is reflected in the x-axis, vertically stretched by a factor of 3, horizontally stretched by a factor of 2, horizontally translated left 1, and vertically translated up 4, what is the equation? So we could just quickly write down what all of these transformations are. Reflected in the x-axis. So reflected in the x-axis means, if we think back to the parabola, that means it's going to be outside the function. So I'll just write that it's outside the function so I remember that it's not the one that's inside. Vertically stretched by a factor of 3. So what does that tell us about the a value? A is equal to 3. Horizontally stretched by a factor of 2. What value is that? Horizontal is k. And if it's stretched, is it going to be 2 or 1/2? Horizontally stretched by a factor of 2. Is a horizontal stretch big numbers or small numbers? We can go back to our name. Stretch is bigger numbers for the vertical, horizontal is the opposite. We can go back to our notes and check. So we said it's a stretch when it's between negative 1 and 1. And so here if it's horizontally stretched by a factor of 2, the k value is 1/2. Okay? Horizontally translated left 1, what's the d value going to be? Inside the function where we have x minus d, what's that d value going to be if it's 1 to the left? Is it going to be positive 1 or negative 1? Negative 1, yeah, because we want it to look like x plus 1 inside the function. Okay, and vertically translated up 4. This is the easiest one, guys. C is plus 4. That one's my favorite. Okay, so we've got all the pieces here. It's nice when you have a question to sort of deal with it piece by piece. And now we can state the function. The function is, it's the absolute value function. The a value is positive 3. And then inside the function, we have a k value of 1/2 and a c value of 4. Okay, so graphing this, I guess we do have another big graphing question. Do you want me to go through this one a little bit more quickly or slowly? I want graph paper. Okay. Okay, so let's go through these transformations one at a time. Okay, vertically stretched by, yeah? That's a really good question. The general form is y is equal to a f at k x minus d plus c. Okay, so everything that's inside the function is horizontal. So we had horizontally translated left 1 and horizontally stretched by a factor of 2, and they're both inside. So because it's happening to the input, it's happening to the independent variable. It's horizontal, and the vertical translation and the vertical stretch, those are outside because it's happening to the output. The function happens, it does its thing, and then you do more to the output. You times it by a value of a and you add c to it. Does that make sense? Did I miss? Yeah, there was this old school thing where they used to do a little line down here, and I think they kind of stopped doing that in most of the mathematical notation, but it's good. Or maybe they just started doing it and they never used to. No, that's good, because if one person has a hard time reading my writing, I'm sure someone else does as well. Okay, so let's do the stretches and the reflections. So there's a reflection in the x-axis. So it's going to be going downwards. Now I'm going to do things in 2 steps. The reflection is going to make it go downwards, and I'm going to do the vertical stretch at the same time. Okay? Are you guys cool with me doing those 2 steps at the same time? So I'm going to stretch it by a factor of 3 and turn it upside down. I got the right reflection this time, right? I could write negative. I'd already dealt with the negative with the reflection, but I can write the -3 here as well. And then that might help me to actually write it correctly when I write the equation. Yeah, that's good. That's a good point. Okay. So it's vertically stretched and it's reflected in the x-axis. The next transformation we should do is the horizontal stretch by a factor of 2. So horizontally stretched, we're going to stretch it outwards towards the big x values, and and maybe I'll just write this is y is equal to -3 absolute value of x. So those are the transformations we applied so far. Now in a new color, horizontally stretched by a factor of 2. So all of our points are 2 further away, 2 times as far away from the y-axis. Okay, and this is y is equal to -3 absolute value of 0.5x. Next are the translations, left 1 and up 4. I'm going to do that in all together at the same time. You ready? Color. I'm going to go left 1 and up 4. Left 1, up 4. 1, 2, 3, 4. Left 1, up 4. 1. This point, left 1, up 4. 1, 2, 3, 4. Not very accurate. Okay. So now we have our final function. Y is equal to -3 absolute value of 1/2 x plus 1 plus 4. Okay?
Now let's look at the domain and range of this function. It's easier to find the domain and range after you have already graphed it. So we have, just so we can see it really clearly, we have this for our final function. And notice that it continues on in this direction. Those arrows are important. Okay? So what's the domain? Well, all the possible x values continue forever. We can always put in x values without any restriction, just like the original absolute value function. So x is a member of the reals. And what about the y values, the range? So for the range, notice that the only values are from 4 and downwards, and the arrows mean the function continues on. So we have y values that continue down into -infinity. So y is a member of the reals, and that means it includes all real values, all the possible numbers that could ever exist on this solid line. If it was a dotted line or just points, then maybe it would be the integers, but this is all real numbers such that y is less than or equal to 4. And that's the domain and range.
So for example 3, we had to factor out the 2 to be able to write the function in the usual form, like k bracket x minus d. We need the 2 to be out front, factored out. So always factor out the k.
So once we factored out k, now our function's in the form where we can read off the transformations. So here we have the k value of 2. So k is equal to 2. That means we have a horizontal compression. Remember, the horizontal is always the opposite of what you'd expect. It's the opposite of the vertical. Horizontal compression by a factor k is equal to 1, 1 over the absolute value of k, which is 1 over 2. Okay, so that's our horizontal compression. And our other transformation is a horizontal translation, and negative 3 tells us it's to the right 3. So now let's graph it. Be easier to do with some graph paper. Okay, so now that we have graph paper set up, okay, so we have to do reflections, stretches, then translations. Or for stretches, you can also do compressions. That's the order we have to do transformations in to make sure that everything works out. So if we do our compression first, horizontal compression by a factor, well, it would help if we had the parent graph. The reciprocal function here. Basically take all the x values and do 1 over the x value. Pretty easy to graph. So this is y is equal to 1 over x. Okay, so the first transformation, I'm going to do it in red. Horizontal compression by a factor of 1/2. So horizontally compressed. So everything's going to be squished in towards the y-axis. Whatever its distance is to the y-axis, the point's going to be half that. And if you get a little confused, just do a table of values. Never touches either axis, it just approaches. And same idea here, all the points are half the distance to the y-axis. So it looks fairly similar, but a couple of key points are moved. Next, horizontal translation, right 3. So usually the x and y axis show us where the function's approaching. It helps us to keep track. It's really helpful to draw a dotted line for where that's moved. So we're going to move it right 3. So that means as it's going upwards towards the y-axis, that's going to be 3 to the right. So I'm going to put a dotted line for the asymptote. And everything else is very similar. So we had a point that's around there, over 1 up a half, 1 up a half. And then here, All the points are moved 3 over. 1, 2, 3. 1, 2, 3. Great. So I go over that one more time, maybe in a better color to see. Okay, so now we have y is equal to f at 2x minus 6.
Okay, so this example is from the textbook, and it asks you to match the equations and the graphs. Okay, we can't see all the graphs right now. I don't want to pinch it too small yet. So a great way to start to approach a question like this is to consider the parent graphs. So obviously the parent graphs have to be the same if they're going to match. So the first function here is called what? Number 1 here, what kind of function is that? You guys remember what the parent graph is? What's the parent graph? Y is equal to 1 over x. Good. So this is the y is equal to 1 over x. It's the reciprocal function, and its possible matches would have to have the same parent graph shape. So there's only 2 possible matches. And then how can you decide from there? I think the easiest thing to look at is the translations. How has this one been translated? We have the x plus 1 and the minus 2. Which transformations are those? What's the 1? It's horizontal translation 1 to the, pardon? 1 left. I believe you. So this is 1 left. I didn't write the whole thing here. Not a lot of space, just so you can see it a little bit. Okay, and what about the minus 2? Down 2. Okay, so if you look at these 2 functions, a and e, which one has been translated once the left and down 2? This one or this one? E, right? Good. So this one is number 1. We can do the same sort of strategy on the others. Look at the parent graph. Which other ones share that parent graph? F. What's the other one with the same parent graph? F and D. Okay. And then from there, how can you decide? Could use the translations again. Yeah. So it goes right 4 and up 3, right 4 and up 3, right 4, 1, 2, 3, 4, up 3. So this one goes right 4 and up 3, and this one goes left 4 and down 1 maybe. So this one must be 4. So you can work through logically the transformations and make the matches on that. Okay. Some people asked for some math help today. It's a lot of new material that we've been doing lately, and there is a test coming up soon. So I'll be in the math help room 236 today at lunch, and as many people who would like to come can come. This is the homework.